Hi, Section 9.2, we're going to talk about intersection unions and compound inequalities. In last section we talked about inequalities are things that are not equal. We follow the same rules as long as you realize that inequality sets, usually, or solution sets, can be infinity, or sometimes we're going to go through some other possibilities. Well, this Venn diagram here on the left side illustrates the first thing we're going to talk about is intersection. The symbol for that is, like, this would be considered A intersects B. This little upside down U is the intersection. So what we're talking about here, if you had this whole set of A right here is in the pink, and this whole set of B is in the blue, where they overlap, this purple is the intersection of those two sets. And we can show that a lot of different ways. If we had, like this intersection here, they show us a set of actual numbers that's a finite set. In other words, there's a specific amount of numbers in this set. When we intersect, we have 4, 5, 6, and 7, and in the other set is 2, 3, 5, and 7. The intersection would be the ones that overlap. In other words, we have a 5 that is in both, and I think that's it. So the intersection of these two sets would be the set of 5, just that number. Well, this example, they go through this and showing the steps a little bit better. But mostly, again, what we're trying to do is realize what intersection means. So in this case, the set of 1, 2, 3, 4, and 5 intersecting the set of -2, -1, 0, 1, 2, and 3. The numbers 1, 2, and 3 are common in both sets. So the intersection of those two would be the set of 1, 2, 3. Now if I drew a picture of these two sets, I could put those numbers in each one of these little circles, but I would put 1, 2, 3 right in that intersection because they're shared between the two sets. So this conjunction is another word they use for this, which is a conjunction, really goes back to an English word for conjunction, which means and. This new sentence is called a conjunction of sentences. So if we look at this situation here too, so intersection and correlate and can cross over in their meaning. Again, you have to be careful with language words because they do mean a lot of different things in English. But we're going to try to define this specifically on how we use the word and. A logical and or a mathematical and they'll talk about. Now in this case we have a -2 is less than x. In other words, what I like to say, remember this inequality symbol basically is coming from this arrow right here on a number line, and that points to the left. So -2 is left of x. And then the other condition here, this intersection, it says and x is less than 1. So or x is left of 1 on a number line. So -2 is left of all these other ones. So, well, let's look at how this would graph out to draw a picture of these kinds of things. So they have these two same inequalities, and they say let's graph and write the interval notation for the conjunction. Well, they show set notation first. They kind of show every way we can illustrate these inequality here. Here's set notation on this side, which is a set of x such that -2 is less than x. Here's the graphing of that, and if you think of this, -2, is it left of all these shaded area? Yes. And that's what x represents, is what's shaded here. -2 is left of it. Notice that there's a curved line on -2 because it doesn't include -2. Because -2 is not left of -2 or less than -2. So we represent that with the parenthesis symbol, and encasing or basically including or covering the side that is shaded. And it keeps going on forever. Well, with interval notation, here's how we'd illustrate that. It means that it includes everything from -2 to infinity. -2 is on the left side of this. It should be a curved line here, where in the case if it did include -2, you'd have a square bracket here and here. Okay, and they tend to use the curved bracket for infinity. Well, these are all the three different ways I could represent this part of my AND statement. Well, the second part, x is less than 1, here again is set notation, is the set of x such that x is less than 1. Well, the graphical version of that would be I'd have a curved line at 1 because it doesn't include 1, and everything left of 1. It's usually a little easier to see when the x is on the left side of this inequality. And I could reverse this too. You know, I could write this one up here on this inequality. This is really x is greater than -2 if I reverse that. Okay? And in other words, all values to the right of -2. Well, here's the graph of this one, x is less than 1. Here's the interval, is it goes to -infinity to 1, not including 1. Well, the AND of these two things, or the intersection of these two, would be where they overlap. And that would be if I took this one and put it over here again, kind of the colors are selected that way. You know, we got blue and red again, and together they make purple. Well, if I overlap that, basically I end up with this deal. It's everything from -2 to 1, not including those values. If I wanted to do this in set notation, you know, it would show the set notation of the set of x such that -2 is less than x, intersecting the set of x such that x is less than 1, would equal the set of x such that -2 is less than x and x is less than -1. Well, both of these have to be true. If I took a value like 7 over here, well, 7 is not less than 1, so it doesn't fit both conditions. Everything in here fits both conditions. Here's that interval notation. Probably the part I don't like about interval notation. It looks like an ordered pair. Okay, so make sure you understand what kind of problem we're working on when you use that kind of notation. So they talk about this. Now, there's another way to write this, is an abbreviated way to write this situation that we run into with ANDs, is I can basically put the parameters of my intersection here, which was -2 and 1, and I can put the variable in the middle if I write this in the right order. So I can say, it kind of goes like this, is I can say -2 is less than x and x is less than 1. Okay, well, both conditions have to occur at the same time, so I can write this in an abbreviated way in a set builder notation. Okay, so when it's written like this, it is an implied AND. Both of these conditions have to be true for this to work. So if they have, for a is less than b, and we say that a is less than x and x is less than b, we can change that to a is less than x less than b. Okay, so these values, if I say this with that left of and right of thing, it kind of makes more sense if you think a is left of all these solutions, which are also left of b. Okay, now I could do an equivalent thing using the greater than symbol or right of symbol. Now notice that we still got to keep things in order. This b is right of x, or all the solutions, and all the solutions are right of B. Okay? And then they talk about this mathematical use of AND, which corresponds to intersection, and the symbol for that again is that upside down U. So here's some examples. Now they're going to give us basically the abbreviated form where I have two inequality symbols in the same statement here. Well, we got -1 is less than or equal to 2x plus 5, which is less, did I say less than or equal to? I meant 2x plus 5 is less than 13. Well, this is an AND statement. We can break this into two inequalities and solve each one individually. So I have to use my properties of addition and multiplication, with the one caveat that I have to watch out for any time that I multiply or divide by a negative. That will reverse my inequality, so be careful with that when you're working with these. Well, they solve this one by adding a -5 to both sides, excuse me. You get -6 equals less than or equal to 2x. Take 1/2 times both sides. They say divide. I would rather stay in multiplication. And you get -3 is less than or equal to x. This one they add -5 to both sides and they get 2x is less than 8. Take both sides times 1/2 and you get x is less than 4. Well, here is my AND statement now, which I can graph these individually. Like here is -3 is left of or equal to all these solutions, right? Well, here's the graph of that. Here's set notation builder again, or set builder notation, excuse me. Now notice that here's that square bracket, because it has the equals portion into this less than or equal to, so it includes -3, and then all these values for infinity. And then in the interval notation, here it is. The square bracket means it includes the -3 to infinity. The other part of my AND statement is the set of x such that x is less than 4. Well, it means x is left of 4 on a number line. Here I use the curved line because it does not include 4, and it's everything to the left. Well, the intersection of those two are the AND statement, right? Where these two things overlap, I end up with this purple, which is going to be -3 is less than or greater than, less than or equal to x, or these things on this side. It is left of, right? And it does include -3, so I use this symbol. All these solutions are that side of it, so I put that here. And then these solutions are also this other border to all my solutions that will work is a curved line because it doesn't include 4, but it's all values left of 4, right, in here. So here is my abbreviated version of that. -3 is less than or equal to x, which is less than or equal to 4. Or -3 is left of or on -3, right, of these solutions, which is then also left of 4. Okay, and then they show all these notations. Caution, it says, we're never going to have a correct answer in the form of a conjunction if our inequality symbols are not at least pointing the same way. I don't want, when I start putting things together and I say, well, this is left of this and the other one's right of that, and those kinds of things, other than being confusing, you're probably on the wrong track. So here's another AND statement, and kind of through the examples we're going to show us some of the possibilities of what can happen with when we're talking about infinities of solutions. So this is already broken out into the AND statement for us. In fact, it is in a way I can abbreviate because the expressions around the x are different, right? So I solve both of these. Here I'd add 5 to both sides, and then I'd take both sides times 1/2, and I get x is greater than, or x is right of or equal to 1. On this side I add -2 to both sides. I take 1/5 times both sides and I get x is right of or on 3. X is greater than or equal to 3. We need to keep that in. Now if I think about graphically how this works, here's the graph of this first one, here's the graph of the second one. When I overlap these things, I don't get border on one side, because this goes off into infinity, this goes off to infinity. So I end up with an infinity on one side of this solution set for this intersection, which is this graph here. It includes 3 and goes off to the right. So the solutions are x is greater than or equal to 3, or x is right of or on 3, right? That's what that describes. Here's the interval again. Square bracket at 3 because it includes 3. So we get this pretty complex beginning and get a pretty simple solution, really, in a sense. Simpler than those abbreviated ones. Well, sometimes there's no way to solve both parts of the conjunctions at once. In other words, we end up with this situation where all the solutions for one of these inequalities would fit into this red area, and all the other ones would fit into this blue area, and we're asking for the intersection, but there's a possibility that they don't overlap at all. So if we look at this one here, where we have 2x minus 3 is greater than 1 and 3x minus 1 is less than 2, we solve these. Think of them graphically, and we'd graph this one, x is greater than 2, which doesn't include 2 and everything to the right. And this one is x is left of 1 or less than 1, doesn't include 1 and it's everything left. Well, there's no overlap here at all. So when I want the intersection of this, basically I get no solution. It's not 0. That's what this is not 0. You know, you see these on smoking signs and stuff like that. It is null set or empty set. It means there are no solutions to this intersection in this case. Now unions are, it's not correct to say opposite in this deal because it doesn't really work like opposites on a number line like, you know, where you have positives and negatives. Unions are, the union, basically these sets are what is our entire set after I put these two things together. Now, it can mean that the intersection we only represent once. And some of the things I do with Venn diagrams, I'll do this a lot with unions and intersections, can be real useful when you're reducing fractions by putting factors of the numerator over the factors of the denominator. Well, all the common factors end up in this place right here. Well, when I get rid of the intersection, I end up with a simplified fraction, but also the union basically gives me the common denominator. If I have two denominators and I'm looking for a common denominator, do addition of fractions, those kind of things. So we are basically been exposed to this kind of thing before in different mathematical methods, really. Well, let's look at what union does. If I want to find the union of this set 2, 3, 4 and 3, 5, 7, I would look at that. Now the numbers are in either or both sets are 2, 3, 4, 5 and 7. Now notice that the 3 is in both sets. I don't say 2, 3, 3, 4, 5, 7, right? That's what this intersection does. So if I put this into this Venn diagram, I would have 2, 3 here because it's shared between the two, and a 4 here. And then I'd have 5, 7. So it'd be 2, 3, 4, 5, 7. Okay? Now, the English word for this, um, in the mathematical sense, is or. I like to talk about if I have one of my kids wants to go to the movie or have some privilege, I can say either you get the dishes done and clean up your room. Well, that and statement makes a big difference, doesn't it? Compared to saying, well, if you want to go to the movie, you will do the dishes or clean your room, right? So in an or statement, basically only one of the conditions have to be true for it to be true. Or in the case of the going to the movie, only one of the things have to be done for my kid to go to the movie. So with an and statement, though, both of those conditions have to be happen, right? So there's a big difference between and or. These are called disjunctions of sentences, and those kinds of things. So let's look at disjunctions, and we need to probably look at this graphically too. In fact, I think this always needs to be graphically, even with the intersections. Now, I'm not saying you have to draw them all the time. I think you can get pretty good pictures in your head of drawing these things. If you're one of those students that likes to draw in class and stuff like that, start drawing number lines and doing that kind of stuff if you want to play with some. Probably not as much fun as drawing something a little more artistic. But if you draw a few of these over and over, you're going to be able to just draw these. You're going to get a mental picture of what these are and not have to draw them out. So, but it is very good to think about what would this look like on a number line. X is left of negative 3. It doesn't include negative 3, right? So it would be look like this on a graph. Here's the interval notation. The other one is we have X is greater than 3, which means X is right of 3 on a number line. Doesn't include 3, so it's that curved line and everything to the right. Here's the interval notation. Well, the union of these, this is a U, which is nice, they use S for union, is going to include both of these. We don't have to worry about intersection as being the only values. It means everything that you've proposed in these two different situations still makes this true. Like this is get the dishes done and this is clean your room. If I said or, I look at that when will this represents whether you can go to the movie or not. I look at, hey, they got their room clean, they can go. Oh, they did the dishes, they could go. They also could have done both, right? And they still can go to the movie. Okay? So then they talk about this mathematical use of the word or to union, or the symbol, this U, and stuff like that. Sometimes call it disjunction. And it must be in at least one of the solution sets of an individual sentence. Okay? Here's an example. And they're going to go through these examples. I'm not going to talk about the solving of all these, but mostly look at these graphs to see what are the things that can happen with a union. So here's another case that's similar to the first one we went through. This one is the red one points to the left of negative 3/4, and this one goes to the right and includes 2, right? X is greater than or equal to 2. Well, the union of these would be both of these on the line. How we do that in set notation is a set of X such that X is less than negative 3/4, or is a key word here, X is greater than 2. Okay? You can do this with the interval notation with the union symbol. A compound inequality like X is less than negative 4 or x is greater than 2 cannot be expressed in an abbreviated form. There's no way that I can show that, because this implies that the solution is between these 2 points. Okay? Now it is possible, pretty rare, that that would occur in a union or an or statement. It is possible though. So these abbreviations mean and, really. Okay? I'd have to be a very, very complex way to get some kind of union to end up with this solution. So example 9 talks about another type here. They got an or again, so it's union. They solve those, they get x is less than 5 or x is greater than or equal to negative 2. So in this case there is overlap, right? And if it was an intersection, it would be very specific. In the purple would only be what was considered overlapped for both, right? Well, in this case, in a union, I can have either one of these things make it true, so everything that touches this and everything that touches this makes this a solution. So we end up with infinity, and if we're talking about a real number line, that's what that double-lined R means, is all real numbers. So we end up with the whole number line being the solution of this. Now I would hope that they could, I would probably expect in this case, this set notation, I don't know if I would accept this as an answer. I would say x, the set of x such that x is equal to all real numbers, right there. Now interval notation and domains. Now going back again, domains are your x values, right? Or what values can I use in my left-right motion? Well, in this case we're talking about that. So now when we're talking about the domains, we're bringing in this idea of a function again. So let's look at this one. We have 5x minus 2 divided by x minus 3. So then the number 3 is not in the domain of G. Why? Because 3 would make this 0. We cannot divide by 0. So we got to make sure in the domain that we represent it in a way that it does not include 3. So in set, we could do this a couple different ways, and it says using domain G, using set builder notation or interval notation. So use interval notation to write the domain of G of x for this function, right? Well, the expression 5x minus 2 is not over x minus 3 is not defined when the denominator is 0. They go through this. So x minus 3 cannot be equal to 0. In other words, 3 cannot be part of this function in the domain. So one way to write this would be the set of x such that x is a real number and x is not equal to 3. It means both things have to be true at the same time. I couldn't put or here. If I said x is a real number or x is not equal to 3, it means 3 would work in that case. Okay? So what they do is they make sure that they separate at this point of no domain. Is I can take everything left of 3 and everything right of 3. So this interval notation represents everything left of 3, not including 3. That's why it's a curved line. And here's 3 is on the left and infinity is on the right. So it's everything right of 3. So they can show it this way with these two curved brackets saying, hey, they come up infinitely close to 3 but do not include 3. Thus we could use interval notation with this union symbol between them. Let's look at example 11 here. It says find the domain of f of x is equal to the square root, that square root symbol, over this this expression 7 minus x. Well, in order for the square root of 7 minus x to exist as a real number, and there's another number set that deals with the other thing, I have to have a positive number underneath this square root symbol. We haven't worked on number systems where we can have like the square root of a negative 4. But I can do the square root of 4. So it's saying this must not be negative. In other words, the way to express that is whatever this is equal to has to be right of and can include 0. So we write an inequality for that. 7 minus x is greater than or equal to 0. Well, add negative 7 to both sides, and then they multiply both sides by a negative 1. Remember that if you multiply by negatives, it reverses that inequality symbol. Okay? So in other words, this domain, or what values will work that I can put into x for this function, will all have to be left of or equal to 7, or less than or equal to 7. So in set builder notation, I'd write that the set of x such that x is left of or equal to 7, less than or equal to 7. Here's the interval notation. Notice that it includes 7 now, so there's a square bracket. Well, good luck on your assignment. Remember, the goal should be on your assignments to get 100%. You got resources if you get stuck or you get a wrong answer on any question in these exercise sets on My Math Lab. You can do the Help Me Solve, and I know it'll change the question next, and it'll take you through the steps, hopefully teach you what you're missing and get you through the process of getting the correct answer. And then it gives you another question, right? And which gives you the opportunity to get that question right. And if you get that next question right, that wrong answer goes away. So you can work on your assignments. Should always be the goal is to, try to get to 100%. I know time sometimes is an issue, but also I would prefer not to spend all that time. I would look through again, or I'd have my book open to the textbook portion of this, or have another window open with the electronic version of the book open, and I would read through these sections a little bit before I start attempting the problems again. And that'll cut down, a lot of times will cut down your time. The other caution I talk to almost all my classes again is not necessarily in this section, but a lot of times you will run into problems where you can find out what the solution is or get the correct answer in another method. And that could be a problem too, because they're specifically going through methods sometimes to build into a more complex task that you can do later. And I see a lot of students get caught by that. They're going like, hey, I got everything right up to this point. All of a sudden they comes into this new stuff and they can't get it right. Well, the prior assignments, they were getting the correct answer, but not with the right method. The method you need to practice a lot of times is a setup to help you get through something different. So looking at the book is a good idea.